Besides the problems we have discussed in the fundamental course, there's one more classical problem that can be solved by greedy algorithm, the Huffman codes for file compression. Huffman code was invented by David Huffman, who was a student taking a double E course. The story is actually quite funny. His professor offered students a choice: either take a final exam or write a paper on finding the optimal code for message compression. And Huffman decided to write the paper. But what the professor didn't say was that this topic was an open problem at that time, and the professor was still working on this problem himself. But Huffman didn't know that, and he solved it with a method that was better than his professor's. And later on, Huffman admitted that if he had known that his professor was struggling with this problem, he would not have even attempted to write that paper. So what does this story tell us? Anytime when your professor offers you the choice that either to take the final exam or to do something else, take the final exam. That would be easier. All right? Well, let's see how Huffman codes work. Let's first take a look at this example. Suppose we have a text, which is a string of length 1000, comprises only 4 characters, A, U, X, and Z. Then if we store it as a normal string of 1000 characters, how many bits will it take? So each character takes 1 byte. 1 byte is what? Is 8 bits. So altogether, it's going to take 8,000 bits to store this string in the normal way, right? However, we realize that we only have 4 distinct characters in that string, and therefore we need only 2 bits to identify them, right? Because each bit has 2 values. 2 bits can represent 4 distinct characters, right? So this is one way that we can encode those symbols: A as 00, U as 01, X as 10, and Z as 1 and 1. So for example, this string can be encoded in this way, and therefore the space taken by the string with length 1000 will be only what? 2000 bits, because 2 bits for 1 character, and there are totally 1000 characters, will be only 2000 bits, of course, plus some space for the code table. So in general, if in a given string we have totally C different characters, for example, in the English we only have like 26 characters, right? And to encode those C distinct characters, we need log C bits with base 2 to do a standard encoding. So this is the result of a standard encoding. But if we want to obtain a better result, if we want to make this resulting string a little bit shorter, then we need to know more information, right? Usually more information means a better result. So the extra information we need is the frequency of each character. That is the number of occurrences of a symbol. So for example, in this string, the frequency of A is 4 because there are 4 A's. All right? And so the frequency for U is 1. For X, we have 2X. That is 2. And for Z is 1. And if we count this extra information into consideration, we can code those symbols with different code lengths, right? So the size of the coded string can be reduced using variable length. Means the length is not a fixed number. Variable length codes. For example, we can represent A by only 1, 0. and U as 110, X as 10, and Z as 111. And with this set of codes, what do we get? So this string will be encoded into a string like this. And if we compare the string length of this one and that one, obviously this solution is better. But here's one question. In which case that there's unlikely to have any improvement at all? Here, if all the characters occur with the same frequency, then there are not likely to be any savings, right? Alright, so the next question is, how are we supposed to obtain this kind of codes? Well, let's first try to represent the original code, that is the standard code, in a binary tree. It's also called a trie. In the trie, all the characters, all the symbols are the leaf nodes. And since they all have the same code length, we build tree from bottom up, like this. And we assign zeros to all the left branches and ones to all the right branches. And therefore, we can obtain the codes like we start from the root. Okay, and from the root to A, we obtain 0, 0, and 0, 1 for U, 1, 0 for X, and 1, 1 for Z. And we define the cost of the code to be the sigma of d sub I times f sub I, where d sub I is the depth of that character, and f sub I is the frequency of that character. And put them all together, what do we obtain? What is the cost of the code? Where d sub I is actually the code length for one character, right? And the code length times its frequency gives the total length of this character in the compressed result, right? And to sum them up, that cost of the code gives the code length of the compressed resulting string, right? So for example, this is the original string. With the standard encoding, this is the result we obtain, and that is what? That is 2 times the frequency of A plus, well, that's 2 for everyone, right? And times the frequency for U, for X, and for Z. And put them all together, we get 16, which means we're going to compress this string into 16 bits. So how about the optimal solution? To represent the optimal code in a binary tree, the tree looks like this. Notice that these 4 characters are actually sorted according to their frequencies, right? A is 1 with the highest frequency, and therefore that one corresponds to the shortest code. It's 0, right? X has the second largest frequency, and therefore it's here. It's 1, 0. U and Z have the same frequency, so they have the same code length. And the cost of this code would be what? Just do the computation and it will be 14, 2 bits less than the standard solution. So how are we supposed to obtain this tree? Well, first let's consider the properties that this kind of binary tree must have. Okay, now say we have this set of codes, and we know that after the compression, the resulting string looks like this. Can you decode it? So hold on for a minute and try to recover the original string. So the answer is this. So what makes this decoding method work? Well, for example, if we replace this one by 0, what do we get? And the solution will no longer be unique. Okay, so here's the trick. The trick is no code is a prefix of another. Prefix means, for example, if we replace 1 by 0, we'll get 1, 0, 0. Then X is 1, 0 that x will be a prefix of u, and that will make this decoding impossible. Okay, that's what this prefix means. Now, here comes your next discussion question. What must the tree look like if we are to decode unambiguously? We know that in order to obtain a unique solution, we must make sure that no character is a prefix of another character, which means in this kind of tree, no character can be placed on the way to another character, which means each character must be a leaf node. It cannot be placed at any interior node, right? So say any sequence of bits can always be decoded unambiguously if the characters are placed only at the leaves. And more than that, the leaves of a full tree. What is a full tree? Full tree is not necessarily a perfect tree. It means all nodes either are leaf nodes or have two children. That's what this full means. There's no degree 1 node in a full tree. Well, why has it to be a full tree? Think about the tree with a degree 1 node, okay? Since all the characters must be placed at the leaves, that degree 1 node is certainly not a leaf node, right? So it must be an interior node. Then what will happen if we delete that node from the tree? We must be able to obtain shorter codes, right? And since we're trying to find the minimum cost, a shorter code means a smaller cost, right? And that's why we restrict it to be a full tree. Okay. And such kind of code is called prefix code. And with that observation, our task becomes to find the full binary tree of minimum total cost, where all characters are contained in the leaves. And so far we are pretty clear about the structure of this tree. And the question is, how are we supposed to obtain the minimum total cost? So the answer is be greedy. And therefore the next question is how? How can we be greedy? Just look at this tree. Let me ask you this question. Shall we build this tree from top down or from bottom up? Think about that. Well, the answer is from bottom up, which means this subtree will be the first one that is built. And since this is from bottom up, it means that these two characters must have the longest code. And therefore, be greedy means we should encode what kind of characters with the longest code. The character with the smallest frequency, right? If they appear only once in the original string, it's okay to assign them the longest code. And if, for example, A appears 4 times, and certainly we would assign A the shortest code, right? So that is the basic idea of the greedy algorithm. So here we have the Huffman's algorithm. And this is the pseudocode. I would suggest you to pause the video for 1 minute and take a look at this pseudocode by yourselves first. So Huffman's algorithm works this way. Let's consider the C characters as C single node binary trees at the very beginning, and then we initialize them in a min heap, because every time we're going to need to find 2 nodes with the minimum frequencies. And then for each character, we're supposed to build a new subtree. So we create a new root for this subtree first. Now be greedy here. Delete 2 nodes from this min heap means we're supposed to get 2 nodes with the minimum frequencies and assign them to be the left and right child of this new node. And the weight of this node will be the sum of weights of its children, where the weight of a tree is the sum of the frequencies of its leaves. Okay, and insert this node back into the min heap. So next time we just repeat again. And the time complexity is what? And first of all, we have this for loop that is big O of C and times what? 2 delete mins, which are log C's, right? So altogether is C times log C if C is the size. Now let's take a look at one specific example. So say we have 7 characters and these are their frequencies. What we do first is to create 7 nodes, record their characters plus their frequencies. Alright, and step 1 is we initialize a min heap. Alright, and the result is something like this. So the first node contains the character with the smallest frequency. Next, we're supposed to create a new node and call delete min twice from this min heap. And we're supposed to get what? 1 and 3, right? Assign them to be the left and right child of that new node. And then the weight of that node will be what? 1 plus 3, that will be 4, right? And push 4 back onto this heap. And this is the resulting min heap we get. So next, we just repeat, right? Create another new node, which is the root of a new subtree, and delete min twice. We get this 4 and this 4, right? And therefore the new root will have the weight 8. Now push 8 back to this heap, and this is what we get. Now I believe that you know what to do next, right? So you can finish the rest of the process by yourselves. I'm going to go through it quickly here. Next, it will be 18, and then what? And then 12 plus 13, and we get 25. And next will be 15 plus 18, something like this. And finally, pop these 2 nodes, and we obtain the Huffman tree, like this. Right? And then we assign zeros to the left branches and ones to the right branches. And this is the set of Huffman codes. So A is, where is A? A is here. So A corresponds to 1, 1, and 1. And E corresponds to, E is here. E corresponds to 1 and 0. And I is 0, 0, and so on and so forth. So the total cost would be the sum of the code length times the frequency. So for A, the code length is 3. It occupies 3 bits times 10 is frequency, right? And for E, the code length is 2 and times 15, and so on and so forth. And this gives the final code length after the compression. So again, this algorithm looks quite simple, but the proof of the correctness is the hardest part. I'm not going to go through the details of the proof, but merely show you the structure of the proof. First of all, we must prove that there is an optimal solution that contains the greedy choice. So here is the lemma. So here C is the character and this is its frequency. And let X and Y be 2 characters in this character set having the lowest frequencies. And then there exists an optimal prefix code for this character set in which the code words for X and Y have the same length and differ only in the last bit. So what does it mean? It means we need to prove this. Say, if there is one optimal solution in which X and Y are not placed at the bottom, then we can always replace those characters and put these 2 characters at the bottom. And we need to prove that this must be another optimal solution. That is to prove that the cost of this tree must be bounded above, be no more than the cost of this tree. And since this tree is an optimal solution, and therefore this one has to be another optimal solution. So when this lemma is proven, it means that we do have that greedy choice property. It means that there is at least one optimal solution that contains our greedy choice. And secondly, we must prove that greedy choice plus optimal substructure is equal to the optimal final solution. So here's the second lemma. Basically, C is the character and this is its frequency. And let C prime be the alphabet C with a new character Z replacing X and Y. And the frequency of Z is the sum of the frequencies of X and Y. And what does that mean? It means something like this. And we denote this tree by T prime. And let T prime be any tree representing an optimal prefix code for the alphabet C prime. So T prime corresponds to the optimal solution of this C prime with Z instead of X and Y here. And then the tree T obtained from T prime by replacing the leaf node for Z with an internal node having X and Y as children represents an optimal prefix code for the alphabet C. So it means that if this T prime is an optimal solution for C prime, then this tree must be an optimal solution for C. Or in other words, if we replace X and Y by Z, then we have a subproblem containing the rest of the characters plus this Z. And if T prime is an optimal solution for this subproblem, then T must be an optimal solution of the original problem. It means that a greedy choice plus the optimal substructure gives the optimal solution of the original problem. And this proof is not so complicated. We can prove by contradiction. But I'm not going to talk about the details. Okay. There's one last question for you to think about after the class. Is Huffman's algorithm the only way to obtain the optimal codes? Okay, so this week you're supposed to get your research project 4 about Huffman codes. All right. The question is basically based on the fact that Huffman codes are not unique. And therefore, taking all kinds of codes as your input, you're supposed to tell which ones are optimal solutions and which ones are not. All right? Have fun.